Alrighty. Got a couple more things. We are discovering how the electrons are organized within the atom itself. Okay? And that's what this purpose of this chapter is. The last chapter, we looked at how the atom was put together, and really we looked at the nucleus, what happened when it fell apart in terms of radioactivity, and in terms of the fact that the nucleus can weigh different things, so we have isotopes, but now we're focusing in this chapter on the electrons. So let's go to the Lord in prayer, and we will continue on with the material. Dear Heavenly Father, I do thank you for this day. I thank you, Father, for your love and your mercy. I pray that you will just give my students strength. I ask this all in Jesus' name. Amen. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. 22 people out of 30. All right. You guys have a busy week, right? Okay. Missing people. So, everybody who was here is going to get a bonus point for being here. Everybody who missed does not get a bonus point. So, sign your name, pass it around. All right? And I will put that on the exam. So you get no penalty for missing, but you do get a disadvantage if you choose not to be here. So let's take a look at a couple of other things. Uncertainty principle. All right, the electrons are in that large volume of space, okay, and we know that the electrons are in quantified areas, okay, because they're transitions, and we calculated that, the transitions from one place to the other only give off certain energies, okay, that are very well defined. Now, we haven't determined what those are yet. As we started looking at the electron and in the smallness of what we were looking at, we get into what are called quantum mechanics, which things don't quite work the same way as the real world. Okay? And so Heisenberg showed that if you actually know the speed of how fast that electron is going, okay, you can know that very well, but you don't know where it is. And if you know where it is, you can't know its speed. Okay? And so there was an equation, and in many cases, our uncertainty about where the actual electron is plus or minus larger than the atom actually is itself. And so we're kind of guessing, quite frankly, even when we get to the math, about where the electrons are and how fast they're moving. And so this equation, I just show it. We're not going to do a calculation with this. So to actually derive where the electrons are around the nucleus, or who is credited with solving this problem is Schrodinger. Okay? He developed a mathematical treatment to account for both the fact that electrons travel as particles and as waves in terms of energy. And it's a whole facet of chemistry called quantum mechanics. And it's a senior level course in which you spend a lot of time and a lot of math. Now, take a look at the picture. Okay? His math did this. It generated a probability of where the electrons could be. Okay? And so it is a probability map of where the electrons could be and every level that we look at. Now, if you take a look at this, you see the electrons' probability is all over the place, right? In general, the shape of the probability cloud that is created is a sphere. Now, one thing that you do not see in this picture that you really need to see is that this probability is not a solid sphere. It's actually a thin eggshell, okay? And so the electron is located in this thin eggshell that has a certain distance from the nucleus, but it's not as well defined as you might want to, as I might make it look when I draw things out. This is one level in which we could calculate. Okay, and what we do is we describe that level as where's the electron 95% of the time. And in this, it's this little thin sphere, okay, a shell that is a certain distance from the nucleus. And that would be the solution in this particular case for where that electron can be. Now, there are multiple solutions. And what we're going to do is we're going to find those solutions. Now, the quantum mechanics and Schrodinger's equations are going to derive for us, okay, the orbitals, and it is going to provide mathematically. We're not looking at the mathematics at this moment in time. We wait until your senior year before you do any of that. We're just going to show you the solutions to Schrodinger's equation. And the solution will give us 3 numeric values of possibilities. Okay? And these are the 3 quantum numbers of a total of 4 that you can have that will describe the location of every electron inside the atom. Okay? The 3 quantum numbers of the 4 that Schrodinger gives us are in the principal quantum number. Okay? And N is that quantum number that Bohr talked about, where we start off with level 1. That is the closest to the nucleus. It has the most energy. And so we could have a level of 1, or 2, or 3, or 4, all the way up to infinity as a theoretical maximum. But you know at some point in time the negative electron and the positive nucleus, if they're too far apart, there's no attraction, the electron falls away. Okay? And that's how far an electron can go away from the nucleus is depending upon how large that nucleus is. The secondary quantum number, okay, is derived from the principal. So whichever value you have as the principal, you are going to get a set of secondary quantum numbers that are possible. Okay? And depending upon the secondary quantum number, I'm going to be able to define what the magnetic quantum number is. So they're interdependent. Depending on the first one, I have a possibility for the second one, and then depending upon the second one, I have the possibility for the third one. Okay? I'm going to show you the patterns of how they are related. The fourth quantum number was added later. It's called the magnetic spin number. And how we will look at these, and I'll give you an example of a quantum number that describes an electron. I could have a quantum number that says 4, 0, 0, plus 1/2. That is a quantum number that describes an electron. This being the N, the principal quantum number. This being the L, the secondary quantum number. This being M sub L, the magnetic quantum number. And this being the M sub S. Okay? So that is one way to show the 4 quantum numbers. At this moment in time, you don't know what values are available. I haven't taught you the rules about how to interpret that, but it can be displayed this way. And basically, that gives the exact address of what that electron is and where it resides within the atom itself. All right. The principal quantum number we've already looked at, 1, 2, 3, 4, 5. The farther away the electron is, the more energy it has, or you can say it a different way, it has less stabilization because the negative and the positive are farther away. And so the largest value of energy stabilization, or the lowest energy electron, is in level 1, closest to the nucleus. Okay? And we know that it's not perfectly even. As we go further out, the energies drop off rather dramatically. And so the possible numbers here, the only thing that you cannot have is a 0 because we start at 1 and we go up there in whole numbers. Okay? So if you look at and evaluate the principal quantum number, as long as it's 1 or greater than 1, you're good, as long as it's a whole number. Now, it gets kind of complicated from here. Not too complicated, but let me show you. Okay? Principal quantum number. I'm going to go ahead and rewrite this in. I said there is a value starting at 1. The L number. Okay? The L number is defined at this. The largest value you can have is n minus 1. So that's the largest. And you have every whole number down to 0. Okay, as possible. So if I have level 1, mathematically, what is the only number I can have in level 1? 0. That's the only one I can have in level 1. But as I go further from the nucleus, I'm going to have more possibilities. In level 2, the largest level I can have, or the largest L, is what? I could have a 1, but I can also have a 0. So I get 2 levels in level 2. 2 possibilities. If I'm at 3, what are my possible values? 2 or 1 or 0. I'm going to do one more. Level 4, they could be what? 3, 2, 1, or 0. Okay. So let me do this. Can you have a quantum number that looks like this? Okay. No. What is wrong? Is the principal quantum number okay? Yes or no? Is 3 possible? Yes. Based upon 3, is that number possible? No. In the third level, the largest I can have is a 2. So this number doesn't exist. Okay? But if I had written, let's say, 4, 0, 0 plus 1/2, does that possibly exist? You can evaluate. Does principal quantum number 4 exist? Is that possible? Yes. Based upon this one, if I have a 4, is 0 a possibility? Yes. Okay? At that moment in time, that's all you can evaluate. Okay, those 2 numbers and how they relate. Now, unfortunately, or fortunately, the secondary quantum number is not always given as a number. Sometimes we give it a letter value. Okay? So the letters are this. Stop. I hate that when it happens. Okay. 1 is a 0. Okay? The 0 can be also termed as an S. For 2, we had a 1 and a 0. The 0 is an S. The 1 value can be given the letter P. The 3 has 2, 1, and 0. The 0 can be labeled an S, so S and 0 are the same thing. A P and a 1 is the same thing. And a D and a 2 is the same thing. What's the last letter that you might have heard of before? An F. So S, P, D, and F. Now we teach you S, P, D, and F because for the atoms we know, that's as far as we can go. All right? But mathematically, Schrodinger solved more. And so the next level would be a G, and the next level would be an H. They are theoretical calculations, but they theoretically exist. We just don't have an atom not that large to get there yet. Okay? And so, if I go back and look at that 4-0 number that I wrote, I could also write that as 4s. That is exactly the same thing as writing 4-0. Okay? Have you seen S, P, Ds, and Fs before? Okay? And so they are the secondary quantum number. Now, what's important about this? Mathematically, the largest one can be n minus 1. Okay? But what's the importance? Okay? The importance for n is distance from the nucleus. Okay? So, nucleus. So that how far away it is. The larger the number, the further away it is. Got that? That's the big idea about this. What about the secondary quantum number? What is the big idea? Okay? It is the shape around the nucleus. Okay? And so what I need to do is show you some of the shapes that these numbers or letters represent. And so what happens in an s orbital, okay, the first one is a shell, and you got the little shell right here, that is pretty close to the nucleus. In level 2, it is a shell or a sphere that's just further out. And if you have 2, you also have 1, so there's a shell or a sphere here and a sphere there. If you have 3s, it is a sphere just larger, further away. All of the s's look like shells or balls. And this is really a better look at it. Okay, remember, it's a probability, so they're bouncing all over the place, but 95% of the time they're going to be in that little shell place. And the value just means it gets bigger and bigger and bigger, meaning the electrons are farther away. All right, the P's. There are 3 different shapes that represent P, and they're dumbbell shape. Here's where the nucleus is. Okay, it is not a sphere around. It makes a dumbbell up and down, side to side, and in front and back. Now, I show you all 3 of them right here, but what really exists is the nucleus is right there, and you have all 3 of the dumbbell shapes around. Okay? That would be, the first time I see a P is in level 2. Okay? I also have a P in level 3. What would level 3 P look like? Exactly the same shapes, just larger, further away from the nucleus. Okay? And so, P's have 3 different shapes. The d orbitals are pairs of dumbbells and one that's a cup. Why do I call one a cup? It's a dumbbell with a donut. See that one? Okay. And so, now, do they look like this, all separate? No, when they really exist, what do? They all collapse, and they're all around the nucleus at one time, and they take up a lot of the volume. But remember, the probability of where those electrons are, 95% of the time, will be in those shapes. Okay? So D have 5 different shapes, P had 3 different shapes, S had 1 shape. Okay, 1 shape, 3 shapes, 5 shapes. What about F? How many shapes? 7. These are them. They are dumbbells, but triple pairs. And then one with 2 dumbbells. Okay? Once we get past this, the math gets really, really complicated, even more so, and they become really strange. Although that's all theoretical, these are the last ones that we actually know really are existing. Okay? Now, I've shown you the first quantum number, right? How far away we are from the nucleus. I've shown you the second quantum number, what shape they are in. What in the world is that third quantum number? Okay? That third quantum number, okay, represents this. Represents this. Okay? An S, or a 0, okay, has a value of, okay, look at this. All right? Between minus L and plus L. Okay? The number of levels is 2L plus 1. So if you have an L of 0, 2 times 0 is? Oh, good. Very good. Plus 1 is 1. It has one space. Okay? Remember the shape? There's only one shape. It was a sphere. The level P has a numerical value of 1. Okay? It is possible numbers are from minus 1 to 0 to plus 1. That's where minus L to plus L. Okay? It has 3 shapes. Each shape is mathematically, one of those shapes is minus 1, one of those shapes is 0, and one of those shapes is plus 1. 2, which represents the D, has 5 shapes. They are numbered minus 2, minus 1, 0, 1, and 2 as possibilities. And then 3 is an F, and it has 7 shapes. They are numbered minus 3, minus 2, minus 1, 0, 1, 2, and 3. So the fact that we have 1 shape or 3 shapes or 5 shapes or 7 shapes come from this mathematical calculation, and each shape has a number associated with it. Okay? Now what does that do for you? Okay? Let's go back to this. 4, 3, 2. The first 3 numbers. Okay? Is this a possible number or not? It all starts with evaluating each one. We start with this one. Is 4 possible? Yes. Good. Is 3 possible? Yes. What is a 3 if I gave it a letter? A D. Okay. And because of this one, if that is 3, is 2 possible? In the level, in the L3, is there a value of M that can be 2? Yes. So that is a possibly correct number. Is 423 a possible number? 4 is good. And if there is a 4, is there a 2? Yes, there's a 2. But in the 2, which is a... Oh, sorry, 3 was an F. If the 2 was a possible, a D, is there a 3 number? No. So that does not exist. Okay? So here's what we now have calculated, an idealized case. In the level 1, there's only one place for things to live, in the S orbital. Okay? But in level 2, there are 2 places. They can live in the S or a P, because I have those available. In the 3 level, I have an S, a P, and a D. In the 4th level, what do you have available? An S, and a P, and a D, and what? An F. All right? Now, in the idealized case, it doesn't matter if you're in level 2 in the S or the P, they should be the same energy value. That was in our thinking. Okay? But what we found out was that it is not. That all the 2s should be exactly the same energy, all the 3 should be exactly the same energy. We found out, nope, that's not the case. Because, do we live in an ideal world? No, we don't live in an ideal world. Okay? There's something that complicates things up. It's called effective nuclear charge. Effective nuclear charge is this, simply. The amount of charge that the electron feels from the nucleus. Okay, so theoretically, let's think about this. If I have 15 positives in the nucleus, and I have 15 negatives on the outside, I've got a 1-to-1 ratio, right? And so each electron should be matched with one positive, and everything should be balanced perfectly, right? And overall, the atom is neutral, okay? But here's the complication. All right, let's do a thought experiment with me. All right, what if I made everybody stand up, okay, and come to the center of the room? Okay, you're all mixed in the center of the room. You got this, right? So you got everybody here in the first row right in front of me, and there's the second row, third row, fourth row. Okay, now watch. I pick a hose. Okay, I got a water hose. And I start spraying the water at you. Who is going to get soaked? Oh, shoot. Who's going to get soaked? Everybody that is right in front of me, the first row. Okay? They're going to get drenched. What about the people in the back row? You may get a little wet, but you're not going to be sopping wet, are you? Okay? What's happened in the atom itself is the same thing. Okay? What happens is the nucleus is throwing out positive charge. Okay? And when it throws out positive charge, the electrons are being attracted. But the electrons that are closer really feel a lot of the positive charge. Okay? And then there's some more electrons in the way and more electrons in the way. What happens is the electrons on the inside shield the electrons on the outside. So not every electron feels a full positive charge, even though I have the same number of positives and the same number of negatives. The ones on the inside feel a lot more positive charge, are drawn in much closer to the center, and there's a lot more stabilization. The ones on the outside are kind of left out. They only feel part of that charge overall, and so their attraction to the nucleus is a lot weaker. Now remember, the energy of every electron is based upon that positive-negative balancing each other out and stabilization. But if you've got all of these shielding electrons, every time you have a level, it will change how much that positive-negative charge is felt, and it changes the energies. And so the effective nuclear charge, or ZEF, is not the same for every electron in an atom. Every electron feels differently, and this is what happens. Each level kind of feels different pulls. And so a 2s and a 2p feel a little bit different. Now, when they feel a little bit different, that means their energies are different. And so 1s, the most stabilization. And then 2s, because of its shape and how it's shielding, is actually a little bit more stable than 2p's. And the 2p is more stable than the 3s, and the 3p is more stable than the... Oh, wait a minute, what happened? Do you see something between 3p? The next level should be all 3's, right? What gets in the way? 4s. That shape comes into play about where it's around that nucleus. The 4s, because it's a sphere, actually gets more stabilization because of its shape than those d electrons. So the ordering gets a little mixed up. It is not always numerical. We get a little bit mixed up because of the effective nuclear charge and the shape the electrons are in. And so when I look at these levels, there are a pattern that exists in terms of how electrons fill into these levels. Now, each of these boxes represents where an electron can live, but that's not quite the case. What we found was that every little level box can actually have 2 electrons. They exist as pairs. And what happens is the electrons exist as pairs, and what they do is they spin in opposite directions. One spinning one direction, one spinning in a different direction. We call that one spinning up, plus 1/2, and one spinning down, minus 1/2. And so for every little box, 2 electrons can live. Okay? And so when electrons are entering the atom, there are different potential places that it can be. And what we will try to do is this. Fill every box starting from the one that is most stable or the lowest energy level, and as we get more and more electrons, then they go up into higher energy levels. Now, how in the world do we find that they were pairs? Well, remember the atomic spectrum? That sodium was a single line. But if you look really, really closely, it is not. It is a pair of lines. Every light source, every one of those light bands comes off. If you look at very, very tiny, they're pairs. Because they are pairs, that's why we think that there are paired electrons. They're all on the same level. They're just slightly different. And that's why we think every level has 2 electrons in them. Okay? The Pauli exclusion principle says that no 2 electrons have the same quantum number. Okay? They're in the same level, distance away. They're in the same shape. Okay? And they can fill into one of those shapes, but they have to have 2 different spins to be able to exist in that space. And we define the last quantum number as either a positive 1/2 or a negative 1/2. Okay? If we write the number, if we actually write it, then the 4th quantum number that exists, that does not exist. Okay? But I can also show this. Okay? If by chance I am in a level, a up arrow is the same as plus 1/2, and a down arrow represents a value of minus 1/2. Okay? Up arrows and down arrows. Now, really, it is not spinning up or down. It's actually the rotation of around their axis. No 2 electrons can have the same exact, so I just already stated that for you. It's a preview. So, here's the principle. Every level S can hold a total of 2 electrons. Every P can hold 6 because there are 3 spaces. Each space holds 2 electrons. Each D level can hold 10, and each F level can hold 14. Okay? Now, something interesting. Look at lithium and beryllium. Okay? Do you see that block there? And then sodium, magnesium, potassium, and calcium? They're 2s. That is where S's are. Look from boron to neon. How many atoms are there from boron to neon? There are 6. That is where the P's exist on the periodic table. Look in the transition metals. How many atoms go across the transition metals? 10. That's where the D's. And down in the lanthanide and actinide series, there should be 14. So the periodic table is organized. S's, or columns of 2. P's, columns of 6. D's, columns of 10s. And F's, columns of 14s. That is why we order the periodic table the way we do. Not just atomic number increasing, but we show you where the S, P's, D's, and F's are by the way we shape that. Okay, so we're going to do electron configurations. And to do electron configurations, we're going to show where every single electron is in a particular atom. Okay? Now there are going to be 4 rules that we are going to apply. Off-balls rule first. You start in the lowest level first and you fill forward. Okay? The lowest level is what's called the ground state. Okay, and we always start with the lowest level. So you always start with level 1, S. And you go from there. Pauli exclusion principle says no 2 electrons can have the same spin. So if I actually show arrows, one has to be up, one has to be down. Okay. Hund's rule. Let's say you're getting into the P level. So let's say I'm doing 2P. Hund's rule says this. The first electron goes into one of them. The second electron goes into the second level. And the third electron goes here. Hun says you have to fill all of those before you start pairing up. So you have to fill one room with one person each before you do pairs. Okay? And then arrows pointing up indicate plus half. Arrows pointing down indicate minus 1/2. Here's where the periodic table works in terms of how they fill. S, P, D, and Fs. You may have learned it a different way though. Okay? And so you may have learned a pattern like you draw them all down and you make arrows. You might have learned that in high school. In CHEM-111, there's a flash that shows you the order of filling. And so these order of filling, what goes before what, is the off-ball principle, which is also, if you just follow the periodic table, what you're going to do. There are 3 ways in which we can ask you to do this. One is the box diagram, where I would show each of the levels and make a box and actually make you draw arrows. That's a whole lot of work, okay? But we can do that. That will test to make sure that you follow Hund's rule, fill one before you double, and the up and down in terms of Pauli exclusion. Most of the time, we're going to make you do this. 1s2, both are there. 2s2, 2p6, 3s2, 3 and 3p3. Why in the world do I end with a 3? Well, if I look at phosphorus, phosphorus has 15 electrons. The first 2 are here. The next 2 are here. I now used 4. The next 6 are here. I've used 10. The next 2 are there. I've used 12. And what happens at the end is I have 3 left. The last 3 are in the P. Okay? And if I actually had to write that, I would write 1 up, 1 up, 1 up. And that's how that would work. Now, that's even long. And so a lot of times what we'll do is this. This is the shorthand called the noble gas configuration. What we say is, all right, you use a bracket and you say, okay, this atom looks exactly like neon. Okay, for phosphorus, neon represents 10 electrons. I then only have to identify the next 5. If I start with group hydrogen is 1s, lithium is 2s, sodium is 3s, so I write 3s, I'll put 2 electrons in there, and then I write 3p, and I have 3 electrons left. And so a lot of times people will use this one because the noble gas configuration, because it is the lazy man's way to do it. Okay. This one articulates a lot more information, shows you every electron and where they are. This one is huge and shows everything, but that's a lot of work. Which one do you use to fill or to make an electron configuration? Read the question. It will tell you what it wants. If you do it the other way, you may be perfectly right, but is CHEM-111 going to say you're right? No. If you don't follow the rules, it gives you the big red box. You don't want the big red box. All right. So again, you know nothing until you try this. Yes. All right, let's try a few. Okay, if I look at silicon, how many electrons do I have to account for in silicon? 14. So I got to put 14 arrows in this thing. Now, how do I know the order of filling? Okay, you can use the periodic table to figure out what's filled first. Okay, or you can use the off-ball rule and draw your little grid and use arrows to determine that. But whatever you do, whichever you do, you have to know the order of filling. Okay, and then I start filling in electrons. So first one, second one, I've used 2, 3, 4, 5, 6, 7. Which rule did I do to do that one? 1 in each box before I start filling. That is Hund's rule. And then I use down arrows for the second ones. That is Pauli's rule. I've now used 10 electrons, 11 and 12, and I'm almost there. 13 and 14. I have now described the silicon in the box form. Okay. If I wanted to be shorthand, which I didn't ask you, I would write it 1s2, 2s2, 2p6, 3s2, 3p, what would I write? 2. And then if I did shorthand, what would I do with that one, the noble gas? What is the last noble gas that I passed? Neon. And that accounts for this part of it right here. So then I write 3s2, 3p6, and the noble gas configuration can be really quick. Okay. The next one, chlorine, -1. What did I just tell you about that atom? That how many electrons does chlorine have? By itself, it should have 17, but the way I drew it, how many electrons does it have? 18. So I just throw in one more electron into that system. So 1s2, I've used 2 of them, 2s2, followed by 2p6, followed by 3s2, followed by 3p6. Okay, I've used 18 electrons at that moment in time. Okay. I want to show you one thing real quick, and it's in your Moodle. If you go to Moodle, you can get this particular tool. You can see hydrogen 1s, helium 2s, lithium, beryllium, boron. Okay, I go through all this, and you can see it will start filling things out. It follows the rules, and everything is cool as I go up here. Potassium is cool. Calcium is cool. All right, watch this. I'm in the 3Ds, perfect. I'm in the 3Ds, perfect. I am perfect, third. What happened? Vanadium is V, and I should put in one more electron, right? Should be in the Ds. What happens? Is that what you would have expected? No. Okay, so there's an error there, or what looks to be an error. What has happened is one of the 4 S's has been promoted into the 3Ds. And you wouldn't have expected. You would have expected 2 of those and then 4 here. Okay? I'll explain this next time, but that is an error in what you would predict. Where is it? Transition metals. If you actually go through this, all of the exceptions to the rules as you go up land in the transition metals and down here in the lanthanide-actinide series. They don't always behave exactly the way that you think they should. And so we get exceptions to the rules all in these areas. These ones don't follow the rules exactly like you would expect. And remember, I said the transition metals don't behave nicely. It is because of the way their electrons are arranged and they have those d electrons, really messes things up. It doesn't play well with everything.